Good morning, everyone. My name is Amol Srinivas Beradar. I am from C2 batch. My roll number is 3332. So today we will be learning about boiling phenomena, pool boiling curve, condensation, and the types of condensation. So basically, what is boiling phenomena? Boiling is the rapid vaporization of a liquid, which occurs when a liquid is heated to its boiling point. The temperature at which the vapor pressure of the liquid is equal to the pressure exerted by the liquid to the surrounding atmosphere. That is called as boiling phenomenon. So first, let's see the one more definition of boiling. So boiling occurs at the solid liquid interference when a liquid is brought into contact with the surface maintained at the temperature surface above the saturation temperature of the liquid. So as you can see, this is a diagram where there is a vessel which has been boiling, in which the water has been boiling, and there's a rod which is which is acting as a heating element. So boiling occurs when a liquid is brought into a contact with a surface at a temperature above a saturation temperature of the liquid. So as we can see here, here there is a pressure of 1 atmospheric pressure. The water is there, and there are some bubbles, and the temperature of that heating element is 110 degrees Celsius, and temperature of saturation is 100 degrees Celsius. So let's move ahead. So let's see the classification of boiling. So boiling is also called as pool boiling, the absence of the bulk fluid flow. Any motion of the fluid is due to the natural convection currents and the motion of the bubble under the influence of bouncy. So boiling is also called as flow boiling in the presence of bulk fluid flow. In the following boiling, in the flow boiling, the fluid is forced to move in a heated pipe over a surface by external means such as pump. So we can see the two diagrams over here. First one is pool boiling, and second one is for flow boiling. So basically, second one is which we used to the water which we use in pipes. You know. So let's move ahead. So this is pool boiling. In pool boiling, the fluid is not forced to flow by a mover, such as pump. Any motion of the fluid is due to the natural convection currents and the motion of the bubble under the influence of bouncy. Boiling regimes and the boiling curve. So this is the equation for boiling curve. Q of boiling is equals to H of Ts minus T saturation is equals to H delta T of excess. So boiling takes different forms depending on the temperature. So here is the excess temperature, which we calculate by surrounding temperature minus uh, saturated temperature. So here is the boiling. Just give me 1 second. Yeah. So here you can see the natural convection of boiling curve. So here you can see the blue color region. We are talking about that. It is called as a natural convection of boiling region. So it is the to point A or the boiling curve. Okay, the bubbles do not form the heating surface until the liquid is heated at few degrees above the saturation temperature, about 2 to 6 degrees Celsius of water. The liquid is slightly superheated, in this case, metastable state. The fluid motion is in the mode of boiling is governed by the natural convection currents. Heat transfer from the heating surface to the fluid is by natural convection. For the conditions of the graph, natural convection boiling ends at the excess temperature of 5 degrees Celsius. So this was about natural convection of boiling. Let's move ahead. Let's see what is knucklet boiling. Okay, so it is shown in the graph between the point A and point C. The bubbles form at the increasing rate at an increasing number of nucleation sites as we move along with the boiling curve towards the point C. The region A to B, it is the isolated bubbles where we can see 5 degrees Celsius is less than or equals to delta T. Excess, which is less than or equals to 10 degrees Celsius. So region B to C, the numerous continuous columns of a vapor in the liquid 10 degrees Celsius, which is less than or equals to delta T, or excess, and again that is less than or equals to 30 degrees Celsius. Point A is referred to as the one set of knuckle boiling, which is also called as ONB, which we can say. So the third region, which is transition boiling region, between it is between the point C and D. When at excess it is increased past point C, the heat flux decreases. This is because the large fraction of the heater surface is covered by a vapor film, which acts as an insulation in the transition of boiling region. Both knucklet and film boiling particularly occurs. The operation in the transition boiling region, which is also called as the unstable film boiling region, is avoided in this practice. So this was about the transition of boiling. So let's see the last part, which is film boiling, which is after the point D. So beyond point D, the heater surface is completely covered by an continuous stable vapor film. Point D, where the heat flux reaches at the maximum, is called as Linden Forest point. Thus, presence of a vapor film between the heater surface and the liquid is responsible for the low heat transfer rates in the film boiling region. The heat transfer rate increases with the increasing excess temperature due to the radiation to the temperature. So let's see condensation. What is condensation? So condensation, when the vapor comes into the contact with the surface of an object kept to a temperature lower than the saturation temperature, it condenses into a liquid with the release of latent heat. The heat transfer accomplished by condensation is also called as condensation heat transfer. The components that utilize condensation heat transfers, that includes the steamline turbine, condenser in use of nuclear power plants, and the refrigerator condenser. The change from the liquid to vapor state due to the boiling is sustained by heat transfer from the solid surface. Conversely, condensation of a vapor to the liquid state results in heat transfer to the solid surface. So let's see the more in detail about condensation. So condensation occurs when the temperature of the vapor is reduced below its saturation temperature. So there are two types of condensation: film condensation and dropwise condensation. So what is film condensation? The film condensation is the condensed wets the surface from the and forms the liquid film. The surface is blanketed by a liquid film, which serves a resistant to the heat transfer. So we can see a first diagram, which is for the liquid film condensation. We can see 80 degrees Celsius the temperature, and also a liquid film at the lower side. So let's see the second one diagram, which is a dropwise condensation, which we can see on the windows whenever the water droplets occurs. So that is an example of dropwise condensation. So what is dropwise condensation? The condensed power vapor forms droplets on the surface. The droplets slide down when they reach a certain size. No liquid film is resist heat transfer. As a result, heat transfer rate that are more than 10 times larger than with the film condensation can be achieved. So let's move ahead. So this is a film condensation. Liquid film starts forming at the top of the plate and follows down under the influence of gravity. Okay, so delta increases in the flow direction x. Okay, heat in the amount Hg is released during the condensation and is transferred through the film to the plate surface. Ts, total temperature of surrounding, must be below the saturation temperature of the condensation. The temperature of the condensate is tat at the interference and decreases gradually to T at the wall. So we can see the graph in which we can see the liquid vapor interference in the start. So we can see a cold plate where the second part, this graph is divided into three parts: velocity profile, temperature profile, and liquid vapor interference vapor V. So the what is acting downwards is gravity over here, we can see. And we can see here the temperature profile, where the temperature of the surrounding was increased in the starting, but it goes on decreasing as we go away from the cold plate. So temperature of saturation is given over here, and this is a velocity profile. So velocity first starts to decrease, and then it goes on increasing. So this is the graph for the film condensation. So let's move to the next slide. So this is a dropwise condensation. So we can see this example of a dropwise condensation of a steam on a vertical surface. Okay. So dropwise condensation is characterized by a countless droplets on varying diameters on the condensing surface instead of continuous liquid film, and extremely large heat transfer coefficients can be achieved when with this mechanism. So small droplets that form at the nucleation sites of the surface grows as the result of continued condensation, collapse into a large droplets and slide down when they reach a certain size, clearing the surface and exposing it to the vapor. This is no liquid film in this case to resist the heat transfer. So that's it. These are the references which I used for making the presentation. And thank you. That's it for today's topic.